Hey guys, it's me, Mystery Man. And you know what? It's been about a week, but you know how I mentioned that I would build a sine and cosine processor? Well, here it is. And you'd probably expect something bigger. I was originally going to build a very fast model, but I decided to change my reasoning a little bit and just give you the concept instead. And this is the concept. Now here's the good news about this device though. It can calculate the sine and cosine in 1 minute and 15 seconds approximately, and that's pretty good. Now there are some things you need to understand about this device. There's a very small range in which we can actually do the angles. So for this thing to be actually reasonable, I decided to make the angles range from 0 to 45 degrees. Now, the good news about that, though, is that's actually just enough to get even the angles outside of 45 degrees. And I'm going to show that to you right now. So, alright, so on the screen I am going to put the results for what the numbers equal, so do not worry. So let's say we wanted to compute 80 degrees. Well, the easiest way that I could think of is making an algorithm. And the algorithm is pretty simple. All we have to do is start with 45 minus 80. And if the answer is negative, then we basically jump 45 degrees and do 90 minus 80. Now that is a negative. And now I could pull the answer off. Now, since 90 degrees is essentially like the highest, so the way the algorithm works that I've created, it's pretty simple. The diagonals will actually have you do 45 minus that angle you just got. But if you have 90 or 270 or 180 and so on, like the cross shape there, then you don't have to do any more. So this 10 right here is our reference angle, and what we can do now is we can input 10. So I'm going to go ahead and pop up my notepad because I've already pre-calculated the radians. I am going to add that as the input in the future because that would be very useful. So we need to add a 1, a 3. I used yellows to section it off so I can actually read this paper, or rather, yeah, the notepad, because it would be very hard to do so otherwise. So I've got that, and then the last number, well, okay, looks like I messed up already. Guys, you didn't see anything, I swear. Okay. Ah, that's it, I think. Let me just go through it. So, yep, there's that. There's that. Okay, there's that. There's that. And, okay, so that's going to be 10 degrees, but I converted it to radians. Now, to convert to radians, it's quite simple. Just do the angle times pi divided by 180, and that'll be a result. As you can see, I will not be able to use 1 as the input because that's above 45 degrees, or rather above the pi over 4 radians. And now we can compute it. So you're probably wondering, well, hey now, the sine and cosine of 10 degrees has nothing to do with 80 degrees, but I'm going to tell you something that's really useful to know. The really useful thing to know that is that if I did 10 degrees, well, then we just get our x and y. If I do 80 degrees, we get our x and y. But here's the difference. Since I've had to interpolate 80, the coordinates simply reverse. So all I have to do is I basically make the sine the cosine, and I make the cosine the sine, and we can actually get 80 degrees. Now, I am going to get into how this hardware works in a second. And yeah, we're almost done. Once this turns off, then the calculation's done. Now, since I'm recording, my frames might be a little weird, but this is actually a very light device. You won't have to worry about it lagging anything. It's pretty small. Like, you can slap this on the bottom of your ALU and you'd be good to go. That's kind of the idea. So, I believe we're done. And the lights will turn off when we're actually done, so let's just give it a second. Okay, so what I'm going to do now is I'm going to read the cosine. Now, since we did 80 degrees, it's actually the sine. So, don't worry. On the screen, I'm going to have the data. So don't worry. You'll see the data like right below the lights, and I'll tell you what they sum up to. Okay, and now I'll show you the sine, which is actually now our cosine of 80 degrees. So basically you could do dual read stuff if you know how to do these reference angle stuff. Okay, so there's that number. Alright, and let's go ahead and do another calculation. So I kind of demonstrated the way to interpolate data outside of my range. But now I can go ahead and do something else. So let's see, let's do another number. I think I'll do 45 degrees. I think it's right enough because I'm sure we want to see a value that's very close to square root 2 over 2. So let's go ahead and do that. So 45 degrees is just 3 of these lights on. And then these will be off, and then this one's going to be on. And then this one's going to be on. And then the last one here is going to have 2 on. Like that. Alright, so let's go ahead and plug it in. And now I will talk about the way this algorithm works. Believe it or not, I just used the Taylor series. Yeah, who'd have thought? I know I could have tried building a coordinate machine, but when I was going through and thinking about how it's, it looped, this is also kind of looped in a way, but this takes only 5 loops to do. When you're doing coordinate, the loops are fast, but if you want a good answer, you have to do like 40 iterations or 20 iterations, and those stack up quite a bit. And plus, you're going to need a huge lookup table. And I did not want a huge lookup table because that's annoying. So I decided to implement the Taylor series. Now, what's actually happening is that I'm actually I actually weaved, sort of, like how weaving is with baskets and stuff. So I kind of weaved the structure of the Taylor series. So I actually have 2 Taylor series running at the same time. I've got one for the sine and one for the cosine. And basically, on the screen you'll notice what I have there, but you'll notice that the sine is an odd function because the powers are odd, and the cosine is an even function because the cosine is an even function. And due to that fact, it's actually really simple because all I have to do is make this top multiplier multiply x to itself over and over to get the powers. It's this bottom one, I'm sorry. And then this top multiplier is the one that does all the 1 over, well, that's a subtract. This is, yeah. This multiplier, though, does the 1 over n factorials, like 2 factorial, 4 all those factorials. Okay, so we did 45 degrees, and this is 45 degrees. You'll see the result on the screen. Now, you will notice that it's approximated. It's not the exact answer. I'll have both the exact and approximated. Okay, so that's the read. Believe it or not, even pocket calculators or your computer in general approximates because of the bit range, so I'd say I'm pretty satisfied. Okay, so those are both of the answers for 45 degrees approximately. And we're going to do one more so that I could talk about some more stuff that I had to do to make this hardware work, because I like talking about that kind of stuff. So let's go ahead and put in my last one, 30 degrees, this one's nice because one of the answers has to be a half coordinate, so that's great. Alright, 30 is 5, and it's going to be 1 there, and then it's going to be 1 there, and 1 there. Okay, so that's going to be 30 degrees. You'll have to just take my word for it, and the outputs will speak for themselves. Okay, so now you're noticing that the Taylor series polynomials, though, they have adding and subtracting. And this is what the cyan and light blue circuit does. It does all the adding and subtraction. So I use a very basic XOR gate. This thing just switches it from subtraction to addition. As a matter of fact, the way it does that is you do 2's complement. And 2's complement is when you invert one of the inputs and also add 1 into the carry. That gives you subtraction. It's just addition, but it's a complementary trick. So, yeah. And you'll notice that we only have 2 memory things because that's all you need for the 2 answers, obviously. But you can notice that they wrap around back into the adder/subtractor, and that's just so that we can keep adding and subtracting to the total. As you can notice, yeah, I only have to add and subtract 5 times, so it's completely fine. So that's good. And it's going to be done now. Like very soon, you'll notice that it'll just close up. I guess it's still going. Yep. Once the light, yep, there you go. So the light's turned off. Okay, so let's see what the cosine of 30 degrees is. Okay, so that's going to be approximately the cosine of 30, I believe. And now you're going to notice that the sine of 30 degrees is 1/2, like the unit circle. So if I go over here, look at that, we've got 1/2, which is perfect. And fine, I'll do this as well, just for the sake of the viewers. So there you go, viewer. I hope you enjoyed that. Alright, so that's it. That's pretty much all I've got to show. I guess I'll get into the program now, sort of. So, yeah, I actually did 2 things. The only lookup table that is used is the one to hold the actual Taylor series polynomial, because how else will you do it, right? But it's a tiny lookup table compared to a huge set of angles that are pre-calculated. You know, from the tangent, that's basically how the quartic works. It uses an approximation from tangent, although it's like, I believe it's like arctan 1/2 and then arctan 1/4 and so on, because it's really close. And then they have a final constant that they multiply at the end. Anyways, so yeah, so believe it or not, the light blue is actually the numbers that are used for the lookup, which is actually reciprocal. It's reciprocal division. So what I did is I used my multiplier as a divider. So if I had, let's say, 1/8, I could pre-calculate that and store it in here and then multiply 1/8. And that's great for functions, that is. So I didn't have to use slow division hardware. That's very nice. Okay, and yeah, these lines just control the subtraction for the polynomial. This writes to the A, this writes to the B, this reads to the A, that reads to the B. This adds 1 at the beginning of the cosine polynomial, you'll notice on the screen. And this starts the sine polynomial with the x. And you'll notice that the busing below is literally just our input, but it hooks up into the adder/subtractor. And that's basically, that's the theory. That's pretty much the theory. And my next iteration of this design is going to be a multi-core design. And the reason why I'd go multi-core is because then I can improve the performance significantly. We can actually start graphing sine and cosine waves on the screen. Or we could perform point rotation around a center. Or, probably one of my more favorite things is we could do polar coordinates with this puppy. So, I can't wait to get to the point where I add this on the bottom of an ALU. Or GPU. I don't even know what we'd add this to. But we'll add it to something useful. Stay tuned. I'll have some new tech for you. And maybe a tutorial for something. You know, I was thinking about building a miniature sine and cosine device using like pure serial. You can leave your thoughts down below if you really want me to do something so insufferable or something like that. Alright, have a good one.